So in the last two videos, we've done a couple of activities. First, there was out for a drive with the car and the bits of tape on the floor, and we took some data, measured the distances and times, and turned the list of numbers into a graph and just looked at the shape of the graph. And then I did my walk the line activity where I had a couple of graphs of distance versus time, and I tried to match the graph in my motion. So the graph is the abstract representation, and I'm trying to match the motion to the graph in both direction and speed. And what I want to do here is then take the next step and show where the equations of motion that you see in physics come from, and you can see that they develop out of first collecting data and turning that list of numbers into a picture, because that's what a graph is. A graph is a picture of numbers, trying to summarize all of these numbers in one picture, and then we can summarize the picture in an equation that we can then apply in different situations, because each graph is a picture of a particular set of numbers, and what we want is a general rule that applies in more than one situation. So let's go back to math class and remember Algebra 1, because a lot of this comes off of or out of Algebra 1. So in Algebra 1, you've got a graph where you've got the vertical axis that we usually call y, the horizontal axis that we usually call x, and you've got a straight line that starts at a point on the y-axis and then just continues to the right. It could be up, could be down, and I've just started that way. Now in physics, instead of having the x-axis, we're going to have the time axis. And instead of having the y-axis, we're going to have some physical quantity that up here that we're going to measure. So I started with displacement. We're also going to look at velocity versus time graphs. And we made one there, and it was almost a horizontal line. And we'll discuss that in a little bit. And then we're also going to have acceleration versus time graphs. And there are other kind of graphs there that we can measure different quantities and how they change in time. So in Algebra 1, if you remember, there is the relationship between how, as you move to the right, what happens moving up or down. Sometimes if you pick a point, then you pick another point, then the question is how far up do I have to go versus how far over? And this is usually called the rise over run, which is a measure of how steep the line is. It's also called slope. So slope, how steep a line is. And you calculate the slope using the formula y2 minus y1, and you got to subtract first, so you need parentheses, over x2 minus x1. And remember, in math class, we've got this is y and this is x, but over here, we're going to have displacement or velocity or acceleration, some other thing. We're going to start with displacement over time. And in math class, you don't have to, you can start anywhere on the line that you want. You can also in physics, but it makes a lot more sense to start with your stopwatch cleared. So then you're always starting with the left-hand point being time is equal to 0. So we're going to take this math formula here, and we're going to apply it to the physics situation, and we're going to use the physics symbols and develop the physics equation from that. So instead of slope, remember slope is going to be the y quantity over the x quantity. Now the y quantity is displacement for right now, and the x quantity is time. So we're going to end up with a meters divided by a seconds, which is going to give us the quantity of velocity. So in this case, slope is going to be the velocity of the object that we were watching move. In the out for a drive activity, it's the car going across the floor. In my walk the line activity, it's me holding the poster board as I move forward and backward relative to the sensor. It's both how fast and in what direction. Because remember, at the end of the walk the line activity, I talked about a positive slope versus a negative slope, and how, if you play back that video, you can see when I had a positive slope, I was moving away from the sensor, and when I had a negative slope, I was moving toward the sensor. The plus or minus tells you direction. Plus or minus gives direction. All right, now how about actually calculating the slope, or in this case, actually calculating the velocity? Now, what we like to do is we like to always start with our stopwatch at time t equal to 0. And then we'll pick another time that we will call t. And in any given particular scenario, we would have a definite time that we want to put there. And we will have gone a particular distance. So we will call this the original position. And then we will call that some other position, and we'll just label that S. So instead of having Y2 and Y1, we have our original and then later on. How about we call that final? We like to do original and final here for our subscripts instead of 1 and 2. So the slope is going to become velocity. And then Y2 minus 1, well, that's how far we went. And if you remember in the walk the line activity and in the out for a drive activity, I started with my sensor or the car at the 0 point. So what we also like to do, not just setting our stopwatch to 0, is we like to move it so that we're always measuring from the 0 point on the measuring stick. So we like to have this guy to be 0 for ease of measurement, because it's always awkward if you start measuring things partway down your ruler. So we like to have that guy be at 0, but we're still going to have to subtract these two guys. So SF minus S0 all over, and we're going to have time 2 minus time 1. So the final time minus the original time. This guy is the original time. This guy is the final time. So we'll have TF minus TO. O for original, F for final. For ease of calculation and measurement, we always, as I've said a couple of times now, we always like to have that guy be equal to 0 and that guy be equal to 0, because that just makes everything easier to deal with. And that makes our equation a lot clearer, because then we just have one distance to worry about and one time to worry about. And what we have here is, well, in physics class, this is a basic velocity calculation. In math class, you would call that your slope calculation. And this is the most fundamental of our kinematic equations, because it deals with motion in one dimension that is constant in speed, which means that there's no acceleration. It's just that constant speed buggy going along in a straight line, and we're not changing anything about this. So that's the first equation that we're going to start with and develop, and we're going to build off of that. And what I'd like to do is show the application of this to a scenario where we're not going to start with a graph. We're just going to go straight from the story to the algebraic application. So we've got Jim walking a distance of 800 meters in a time of 5 minutes. Now we have 3 kinematic variables here. We've got velocity, we've got displacement, and we've got time. You get the velocity. If you look at the question here, how fast, that tells you what you don't know. So that gets a question mark. 800 meters, meters is a distance, so this is 800 meters. And then I told you time of 5.0 minutes. And you need to keep in mind that M all by itself is meters and MIN is minutes. Then the question is, how fast did he walk? So we've got our list of givens and what we want to find out. Our fundamental kinematics equation is velocity is displacement over time. And because I'm asking for velocity in this scenario, we're going to use this version of the equation. We don't need to rearrange it. And then we can plug in numbers where S in this particular scenario is 800 and time in this particular scenario is 5. And when we divide, we come out with 160 meters per minute is how fast Jim is walking. Now for our significant figures, we've got 2 sig figs here, and we've only got 1 here. So we're going to have to round this, round to 1 sig fig because of that 800. So that 160 rounds to, he's walking at about 200 meters per minute because 160 rounds up to 200. All right, in our next assignment, what we're going to have is several scenarios where we have a story that I'm going to want you to turn into a graph and then do this kind of calculation to find the missing piece of information, which will most likely be the velocity to start out. All right, we're going to be moving away from the graphical analysis towards the algebraic analysis as we progress through kinematics now.